Hello, thank you for joining us. We're excited to have you as we celebrate 15 years of Amazon EC2. Let's talk about autonomous vehicles. Compute, and particularly high-performance computing, is essential for autonomous vehicle development. Amazon EC2 provides the foundational compute needed for our customers engaged in developing these technologies. I'm Vijita Chekuri, Global Business Development Leader for Autonomous Vehicles and ADAS at AWS. Joining me today is Varun Ramakrishna, Director of Perception Engineering from Aurora Technologies. Developing advanced driver assistance systems for today's vehicles, or ADAS, and autonomous vehicles of the future is a promising but challenging process across multiple functional dimensions, including technology, compliance, reliability, security, and capital investments. In this session, we'll learn how AWS is helping accelerate ADAS and AV development with global hyperscale infrastructure and the latest in technology offerings, particularly compute. Hear from Aurora, an industry leader with a vision to transform mobility, on their experience developing the Aurora Driver, an L4 autonomous driver system on AWS. We know that the automotive industry is undergoing a transformation unlike anything it has faced in the past. Driven by mega technology trends like ubiquitous connectivity, cloud computing, cognitive technologies like speech and touch, and finally, artificial intelligence, there is a distinct shift in consumer mindset. They're pivoting away from traditional automotive purchase reasons and focusing more on experiences and personalized interactions. The mobile revolution has created expectations that their digital lifestyle should follow them wherever they go. For automotive industry, the convergence of all these factors is unlike anything they have experienced in the past, leading to the fundamental way in which the customers are purchasing, driving, and owning cars, and forcing the entire industry to rethink their brands and business. Automotive companies are looking to become mobility services providers. The industry's strategic priorities have been termed CASE or ACES for short, referring to connected, autonomous, shared, and electrification technologies to cater to changing consumer expectations. Responding to these changes requires a new model of engagement. Many companies are looking at the cloud as a way to double down on investments that support their core mission for their company and differentiate it from the competitors. As a result, they're looking at new ways to innovate that allow for more experimentation and more customer engagement. And they're doing it in a way that meaningfully reduces their security and compliance risk. Self-driving cars represent a moonshot for artificial intelligence and machine learning. Reports predict that autonomous vehicles will contribute to some $800 billion of savings annually in economic and societal benefits when AVs are fully deployed, of course. The benefits will come from cost savings related to reduced crashes, fuel efficiencies, and better access to transportation. Although the headlines are dominated by self-driving cars in the past few years, the road to autonomous has been underway for decades now. Starting in the 1980s, automated features are being developed and becoming commonplace in today's personally owned vehicles like adaptive cruise control and emergency braking. As we think about realization of an autonomous future, we think about it in three different time frames. Today and in the near term, ADAS will continue to be the focus of OEMs and Tier 1s, and they're developing and refining the sophistication of ADAS, which is bringing them revenue today and compliance with regulations for the production vehicles, while they continue to invest in parallel programs or in startups for fully autonomous vehicle development. In the medium term, which we loosely define as 2022 to 2026, we're still seeing ADAS going strong, but additionally, we also see some of the first driverless autonomous vehicle use cases being deployed. Specifically, we see that coming from limited operational design domains, or ODDs, like geo-fenced mobility services, where the cars can confidently navigate the roads and the environment, to goods delivery with use cases like long-haul trucking on highways to last-mile delivery of goods. In the long term, timing is very much TBD, we will see commercial scaling of autonomous vehicles. So, how do autonomous vehicles work? ADAS and AV vehicles are fitted with different sensors that serve different purposes and cover a variety of ranges and depth and perception axes. The higher the level of automation, the higher the sensor count on the vehicle. Simply put, these sensors help the perception systems perceive the surroundings and position the vehicle relative to the surrounding environment. The perception system provides this information to the path planning system, which then decides the next steps and ultimately controls the vehicle. Autonomous or ADAS functionality happens real-time in the vehicle in a very self-contained manner. The AI models that are deployed in the vehicle to make this happen, however, are developed over an autonomous development tool chain that works with massive amounts of data and compute to derive the exact algorithms. The maturity of the technology to accurately predict and plot the course and the complexity of the tool chain to collect, manage, label, train, simulate, validate, and verify the data to create the models pose multiple challenges to companies pursuing the development of autonomous vehicles. Based on our experience with our customers, the key underlying challenges that they face in developing autonomous technologies are somewhat universal. The hyperscale nature of the infrastructure needs, associated costs, agility in development, speed to market, complexity of the various tools involved, and most importantly, security, privacy, and compliance. AV development requires specific expertise as well, which presents a personal limitation, and companies need a lot of support to execute their workloads well, whether it's optimizing and tuning their training jobs or enabling higher scale of simulation work. During the development phase, customers typically have geographically distributed test fleets that collect tens of terabytes of data per day. This data quickly scales up to petabytes for companies with a decent sized test fleet, anywhere from 15 and above. All of this data needs to be collected, curated, managed, and cost efficiently stored. And the data pipelines need to be agile to be iterated upon for model development, training, simulation, and validation over thousands of cores of specialized compute. And this development, test, and validation is iterated multiple times prior to production release of the driving models. Agility and speed of iteration is key for time to market for autonomous functions, especially ADAS programs, which are they need to be more production ready. Our customers need global, secure, data sovereignty compliant, hyperscale infrastructure with the latest in AI and ML and computing technology. And this is where AWS can help. At Amazon, we have been working with autonomous systems, robotics, and machine learning for over 20 years, starting back with our recommendation engine for the Amazon.com site in the 90s. Machine learning and AI is at the center of Amazon business. This experience translates well to autonomous vehicle segments as well, as AI and machine learning is at the center of autonomous vehicle development as well. We work backwards from the customer to innovate new services and features on their behalf to help them with that journey. There are many versions of an autonomous development workflow, and this slide here shows our version of a super simplified workflow that provides an overview of the type of activity associated with developing autonomous vehicles. As mentioned before, highly automated and autonomous driving happens real-time in a self-contained manner through the driving models deployed in the car. While the driving happens real-time, the driving models are iterated over the complex development and validation tool chain prior to being deployed into the vehicle. The workflow activities are centered on the data collected from specially instrumented test vehicles that are fitted with various perception sensors. Raw data is captured and ingested from the vehicles into a centralized storage, or what we refer to as an autonomous vehicle or AV data lake. In the data lake, the data is available for further refinement, transformation, and analysis. Some of the processing can take place on the edge before the data is ingested, but much of it happens in the cloud. Once that data is in the data lake, it can be cleansed, PII obfuscated, labeled, and used to develop maps and machine learning models. Those models, once developed, are tested through simulation and validation using both raw, refined, and in some cases synthetic data. Once the models are validated, they're deployed to the vehicles for testing in the real world. This workflow is not meant to detail every step of autonomous development, but captures the key workloads. The various phases of the workflow are also not serial, and there are many complex interactions amongst the various phases. This is a result of constant algorithm, model, sensor, hardware, and platform tuning needed for these systems from globally distributed development teams. Traceability of workflows and their complex interactions is a key need from compliance and homologation standpoint, which is a process for vehicle production approval. Due to the hyperscale nature of the autonomous workloads requiring toolchain accessibility to globally distributed development teams with added security, appropriate access controls, data privacy, and residency requirements, cloud is best suited to provide the foundational infrastructure and technology for the autonomous toolchains. AWS offers unprecedented breadth and depth of first-party services that our AV customers depend on. Our unparalleled pace of innovation, scale, and global reach enables compute-intensive AV development cycles to be compressed and cost-optimized more efficiently than elsewhere. Prominent companies like Mobileye, Aurora, Torque Robotics, and Lyft are building autonomous driving models and HD maps on top of AWS. Our partner ecosystems provides end solutions for key workloads like simulation and scenario generation, for example. Some of the key first-party services that our AV customers leverage are shown here. And it's not inclusive of every service, but a representation of the key ones. We have first-party tools, reference architectures, open source code, and best practices for the various phases of the workflow, both first-party and third-party, and we continue to innovate on the necessary services to solve customer pain points for autonomous development. Customers are building agile, cost-efficient, reusable tool chains with the latest in innovations across edge computing, machine learning, AI, compute, and other bleeding-edge technologies on our cloud. Data, compute, and AI and machine learning represent the key aspects of the infrastructure and technology needs for autonomous vehicle development. EC2 provides compute and specialized compute needs to act on the AD big data and leverage AI and machine learning pipelines and frameworks to derive the driving models that automate the vehicles. Let's start with the foundational services. AWS has the largest global infrastructure footprint with 24 regions, 77 availability zones with one or more data centers, and 216 points of presence with 200 plus edge locations. And this footprint is constantly increasing at a significant rate, serving globally distributed customers and their AV fleets. The global infrastructure provides the basis for the massive data ingestion, storage, and management. Here's a simplified list of some key AWS services used for high-performance computing workloads, of which AV development is a subset. As mentioned before, data and AI ML with specialized compute are cornerstones for autonomous development. From data ingest to storage, optimization of storage for high-performance computing, orchestration and scalability of AI ML workflows for simulation and training, and finally, secure and managed access across the unified data pipelines, we have many first-party services that help with the entire development life cycle. With the amount of data AV companies deal with for autonomous vehicle development, storage is one of the biggest cost drivers. To start with, there are various ways in which terabytes and petabytes of AV data can be moved into AWS storage for further processing and refining. The most popular online data transfer mechanism is through AWS Direct Connect. With 10 gigabits per second and 100 gigabits per second direct connect networking, AV data can be quickly transferred to the data lake to be pre-processed, trained, and simulated. AWS Snowball Edge device service is what our customers use today as a stopgap method until Direct Connect is installed or for offline data transfer scenarios. With 80 terabytes of usable storage, Snowball Edge provides the right storage form factor to transfer data from the data logger storage in the vehicles to the AV data lakes on AWS. Amazon S3 provides the most cost-efficient storage with 6 storage class options. S3 provides the most classes of storage of any cloud, and you can configure your data storage based on the frequency of access, durability, and availability requirements. AWS now has a new storage class option if you do not want to think about access pattern or have data with unknown or changing access pattern called S3 Intelligent Tiering that automatically does this for you. Coming to machine learning, AWS has the broadest and deepest set of machine learning capabilities for builders of all levels of expertise. At each layer of the stack, we are helping in removing the undifferentiated heavy lifting so the development teams can move faster. At the top layer are our AI services. This is for developers to easily add ML to applications without needing much ML skills. These are pre-trained, they're sort of grab and go, and for quick wins. And most startups we work with are deploying these into production in a few hours to 2 weeks, depending on complexity. As previously mentioned, Amazon SageMaker provides every developer and data scientist with the ability to build, train, and deploy machine learning models at scale. SageMaker removes the complexity from each step of the machine learning workflow so you can more easily deploy your machine learning use cases, anything from computer vision to customer scoring. And at the bottom layer, expert practitioners can develop on the framework of their choice as a managed experience in Amazon SageMaker or use the AWS Deep Learning AMIs or Amazon Machine Images, which are fully configured with the latest versions of the most popular deep learning frameworks and tools. Our AV customers typically fall in this category of machine learning and AI model development. Within SageMaker, SageMaker Ground Truth is a fully managed labeling capability that provides 30 plus computer vision workflows for 2D image labeling tasks like semantic segmentation, bounding boxes, instance segmentation, etc. It also provides production-grade LiDAR 3D point cloud for object detection, tracking, and segmentation. Based on our discussion with AV customers, they need scalability, visibility, and control in their data labeling pipelines. SageMaker Ground Truth provides assistive tooling to increase speed of annotations using ML capabilities like Dexter, interpolation, and more. It also provides auto-labeling capability to reduce cost of labeling by up to 70%. Customers can continue to use their internal teams or use 8,000 plus annotators available via AWS Marketplace. All capabilities are pay-as-you-go with no lock-in, and customers can qualify for volume discount. Once the data is labeled, it can then be fed into the machine learning pipelines. Last but not least, compute. Here are some of the compute-intense workloads for AV development. Courtesy of Zoox, this video depicts an autonomous vehicle making a right turn at a stop sign in downtown San Francisco. As you can see, the AV is able to identify and yield to pedestrians in pink boxes before making the right turn, and is also able to identify other vehicles on the road depicted in the blue boxes. It takes an incredible amount of data processing and compute to make this happen. Some of this happens in the car in real time, but the actual model training and validation typically happens offline in the cloud as the compute resources required are immense, potentially thousands of GPUs for machine learning and tens of CNNs or convolutional neural networks, and millions of virtual CPUs for software in the loop simulations. Simulation and training are the top two AV workloads that are hugely compute intense. There are two types of simulations, resimulation or replay, and synthetic simulations or simply simulations, as is shown here in the Zoox video. Other top compute intense workloads are labeling, data management, including scenario extractions. Let's go a little deeper on compute needs for AV development. AWS has comprehensive and broadest and deepest range of choices for compute platform. We have families of instances designed for virtually any workload, whether you want to optimize for raw CPU cycles, memory per CPU, or even a high I/O storage and powerful GPUs. Each of these instance families can further be customized with choice of processors, type of storage, ultra-high speed networking, and even bare metal options. Add in other options like Amazon Elastic Block Store, and we have over 400 distinct instance types, giving our customers the most choice and flexibility when it comes to compute. Here's an overview of compute resources within the EC2 instance types. Choosing the right instance is very important for optimizing the price performance for your ML training, simulation, and other HPC workloads. More broadly, we have the widest range of compute instances, and we provide massive amounts of capacity, enabling you to reach the simulation scale needed for the development. For simulation and validation particularly, we have seen our customers use C, M, and sometimes R-class instances for autonomous vehicle development. NVIDIA-based GPU instances of P3, P4, and G4 are commonly used for AV training and simulation use cases. P3 and P4 in particular for training, and G4 for perception and simulation sort of use cases. We have also announced new hardware from AWS's own Annapurna Labs. AWS Trainium is a machine learning training specific chip that when released will offer the most teraflops of any compute instance in the cloud. Autonomous vehicle workflows are expensive to develop and manage. For example, the amount of compute needed is in the millions of hours for CPU-based compute and tens of thousands or hundreds of thousands of hours per month for GPU-based compute. So as your cloud environments and usage scales, optimizing your costs and right scaling the workloads becomes essential. A mix of reserved instances, on-demand, and spot instances to best match your utilization will optimize AV workload for both performance and cost. Reserved instances is the best way to secure compute capacity for your steady-state training and simulation needs, and all other AV needs, of course. Any excess of compute needs can be met with the elasticity of on-demand instances and even spot. Spot instances allow customers to take advantage of unused EC2 capacity in the AWS cloud for up to 90% off of on-demand pricing. As spot can be reclaimed with a 2-minute warning, it is perfect for fault-tolerant, flexible, loosely coupled, dynamically scaling, and stateless applications. Customers should consider spot instances if their workloads are time, instance, and are location flexible. Essentially, any application that can have part or all of the work paused and resumed or restarted can use spot. Though it can be reclaimed with a 2-minute warning, only 5% of the spot instances were interrupted in the last 3 months. To give customers more choice on how to balance performance and cost, spot instances are integrated with AWS services such as EC2 Autoscaling, EMR, ECS, EKS, CloudFormation, Fargate, SageMaker, and AWS Batch. They can also be launched with integrated third-party services. These integrations allows customers to seamlessly use Spot in their existing workloads, helping them not only to lower costs, but increase their access to compute resources. To summarize, we have tooling that supports every aspect of autonomous and ADAS development processes, from devices and networking reach to support the acquisition and ingest of data, to compute variety and capacity to expand use case applicability and ability to scale. The first thing we provide is cost optimization functionality to ensure you're not paying more than what you need for your given workload. Let's take storage for example. Each storage class has a different price based on how frequently you are expected to access the data. We have S3 intelligent tiering, which optimizes your storage class based on usage patterns. If you are not accessing certain data frequently, you can automatically begin saving as intelligent tiering shifts to a cheaper storage class. With petabytes of data, this has been very impactful for our customers. We have volume discounts and private pricing agreements, which help address the cost challenge. Before you take the public pricing for your TCO calculations, please reach out to your AWS representative so we can have a holistic discussion on cost efficiencies so we can provide the pricing that is customized for your application. We have many customers running ADAS and AV workloads in production on AWS. Across petabyte scale data ingestion and storage, deep learning, HD map generation, large-scale resimulation, simulations, machine learning, and overall end-to-end cloud-based development, our customers leverage AWS extensively to accelerate their autonomous vehicle development. Now, let's hear from one of our most important customers, Aurora, and Varun Ramakrishna, Director of Perception Engineering from Aurora, about their autonomous vehicle technology development they call Aurora Driver.
Thanks, Vijita. I'm Varun. I'm the Director of Perception at Aurora. And I'm really excited to talk to you about who Aurora is, our mission, the benefits of self-driving technology, the Aurora Driver, our partnership with AWS, and how it's enabling a new paradigm of technology development for the autonomous vehicle industry. Aurora was founded in 2017, and we are led by three of the world's leaders in self-driving. From left to right, here's Sterling Anderson, Chris Thompson, and Drew Bagnell, who together hold an unprecedented understanding of machine learning and the path to our self-driving future. Chris, our CEO, has been instrumental in building successful autonomy programs, including Google's self-driving project, now known as Waymo. Sterling, our CPO, has expertise in developing and launching unprecedented products, including Tesla's Model X and Autopilot. And Drew, our chief scientist, has been a pioneer at the intersection of machine learning and robotics for decades. Next, I'd like to talk a little bit about our mission. Our mission, simply stated, is to deliver the benefits of self-driving technology safely, quickly, and broadly. This drives our values and culture and guides our approach to technology and our partnerships, including with AWS. What are the benefits of this technology? Increased safety. The technology can reduce fatalities or serve injuries by eliminating driver fatigue and distraction. Per the WHO, 1.35 million people die each year in road fatalities, and 94% of incidents with trucks are due to fatigue and distraction. Transforming logistics with improved efficiency and capabilities, expanding access to transportation for those with disabilities that make traveling difficult, and improving lives by giving people a bit of time back on their daily commute. And to bring this technology to life, we've partnered with some of the world's largest manufacturers to bring it to market. We have tremendous focus to deliver the Aurora Driver, and we rely upon the expertise of our partners to develop and deploy safely, quickly, and broadly, including some of the world's largest manufacturing companies. For autonomous trucks, we've partnered with two of the largest truck OEMs in PACCAR and Volvo Trucks, which represent more than 50% of the trucking market. And for autonomous passenger cars, we have partnerships with several OEMs, including Stellantis, Volvo Cars, and most recently, Toyota. We also have partnerships with networks like Uber to launch our autonomous ride-hailing business. At the core of our product is the Aurora Driver. And the Aurora Driver is the software and the hardware, like sensors, that allow us to safely operate any vehicle without a human driver. We've developed the Aurora Driver to be vehicle agnostic, meaning it's versatile and scalable, and we've already integrated this into numerous different vehicle types, ranging from a sedan to a Class 8 truck. There are three aspects of the Aurora Driver: the self-driving software that runs on the car, that has modules like perception, planning, and mapping; the self-driving hardware, such as radars and our FirstLight LiDAR and cameras; and the data services and platform that's required around driving an autonomous vehicle. In the next slide, you'll see an example of the Aurora Driver in action. In this video, we see the Aurora Driver in action, autonomously driving a truck on a highway in Texas. The boxes in blue show the Aurora Driver detecting and tracking other actors on the road and responding appropriately to them in heavy to moderate traffic. Next, I'd like to talk a little bit about how we approach autonomous technology development and produce an autonomous system that behaves in this way. Developing the Aurora Driver relies on 3 pillars. The first is high quality, high integrity, and high performance sensor data that is labeled with high accuracy. All our platforms are equipped with multimodal sensing capabilities, including radar, conventional LiDAR, cameras, and Aurora's in-house FirstLight FMCW LiDAR. This gives us unparalleled sensor coverage at near and far ranges that enables highway speed driving in challenging operational domains. Our fleet generates petabytes of data that's used for triage, labeling, and training machine learning models that feed into a data-driven development workflow. And all of this is enabled by an underlying hyperscale infrastructure that leverages several AWS technologies, S3, EC2, and RDS, among many others. And this allows us to operate a reliable, scalable, and highly efficient autonomy development workflow. The second pillar of our development is an onboard machine learning powered architecture that's capable of continuously improving with data. The Aurora development process is powered by a large-scale machine learning production workflow where we follow a 2 to 3 week operational cycle where we operate our fleet on the road, collect data, triage events, label them, and flow this data back into our labeled data sets. And then the cycle continues by training new models based on what we've learned, and then measuring that performance both offboard and onboard, and then the cycle repeats. Central to this is an onboard architecture that is fundamentally data-driven and capable of improving with new data. Our onboard architecture consists of a modular constellation of deep learning models that perform multiple functions across the stack, including object detection, tracking, forecasting, and decision-making. We leverage AWS's SageMaker and EC2's flexible, customizable, and highly available accelerated computing instances for large-scale distributed machine learning that enables deployment to the vehicles and rapid experimentation. The third pillar of development for the Aurora Driver is evaluation, that is, measuring and validating the performance of the driver. At Aurora, we place a large emphasis on virtual testing. We believe a single virtual mile can be just as insightful as thousands of miles collected on the open road. In the animation that you see on the right, each pixel represents a test of a particular capability that the driver is trying to execute in the real world. We memorialize these tests and create variations of them. And in this graphic, we're showing 40,000 unique variations of test scenarios that are run offline in the cloud on each change that we make during development. Our offline tests focus on specific capabilities and scenario edge cases that we see on the road and that we can build variations on. Here's an example of a tool that we've built to test perception, where we can select individual actors on the scene and set conditions on the actors that they need to pass in order to pass the test. We collect thousands of these tests from our on-road operation, and then via simulation and other methods, we create further variations, thereby assembling a massive battery of tests that are run offline and ratchet our progress and provide performance signal. The virtual tests in our platform perform multiple roles. One is CI/CD. Every change that we try to land to our autonomy system is gated by a battery of such virtual driving tests that play back thousands of instances of what the car sees or would see on the road and runs the system as it would on the car to prevent regressions. Performance validation is another use. We measure the system's performance across a large set of tests and variations that provide coverage across a wide variety of scenarios that we might encounter during driving, in aggregate amounting to several million miles of driving during development. Testing such a system is highly data intensive and compute intensive. We run the autonomy stack as it would run on the car, and data intensive because we operate on very heavy sensor payloads, including radar, LiDAR, and cameras. Here we leverage Amazon's EC2 and several other foundational AWS technologies to enable massive scale virtual testing of autonomy software, thereby supercharging autonomy development. In this short talk, I spoke about Aurora, our mission, our development process for autonomous vehicles, and how our partnership with AWS supercharges our development velocity. I'm excited to work on this revolutionary technology, and I hope you enjoyed this talk. Thank you, and back to you, Vijita.
Thank you, Varun. That was wonderful, and thank you for the partnership. And thank you, everyone, for listening to this session, and hope you found it helpful. Please reach out to me with any questions on the session or any inquiries for AWS on autonomous vehicle development or ADAS development. Our AV team at AWS is eager to hear from you. Thank you and have a wonderful rest of the day.